Hello everyone, my name is Brian Scholes, an event manager with AusIMM, and I'll be facilitating today's webinar, The Changing Landscape of Minerals Processing Projects. I'd like to thank you for attending the live webinar today and those who are viewing the recording. Just a few housekeeping items before we get started. Everyone is on mute today to avoid presenter distraction and noise feedback. We will have time for questions at the end of the presentation. Should you want to ask any questions, you can type them into the question box available to you on your side panel. A copy of the webinar will be sent via email to everyone who is registered in the next few weeks. We'll also have a quick exit survey when you leave the webinar. I'd now like to introduce today's presenters from Ausenco. We have Greg Lane, Chief Technical Officer. We have Grant Ballantyne, Global Director, Technical Solutions. Tim Viscara, Technical Consultant. Rajiv Chandraman, Global Technical Director, Operations Optimisation. Over to you, Greg.
Thank you, and welcome to this series. Ausenco is excited to partner with the AusIMM to deliver a webinar series that addresses the challenges that are faced by our mineral processing industry. Today's webinar will present some simple solutions and that all add value and address those challenges. I'll provide an introduction to the series. Grant Ballantyne will discuss, just excuse me for a minute. We'll discuss how preconcentration can be used to improve the economics of operations and reduce tailings liabilities and reduce water consumption. Tim's going to talk about some real-life examples of how geomet's used, and Rajiv Chandramohan will discuss how smarter process control and optimisation solutions will achieve increased revenue and immediate returns on investment. And we'll wrap up with a Q&A session. The webinar series is going to focus on one of the key values at Ausenco, and that's how do we provide maximum value to our clients across project life. So it's not just about the front end, it's about the conception, the operation, design, engineering, all aspects of project life. The key requirement is that we recognise and agree what value is for a project with our clients and with all stakeholders. The value will include a combination of schedule, capital, operating costs, performance, culminating in revenue-related measure, typically NPV, but often varies. So whether the activities is a desktop study or it's a feasibility study or providing services for plant optimisation, the model of what value looks like is always required. Too often I see series delivering poor results when the outcome that we should have been recognised at the front, or the issue should have been recognised at the front of the study and addressed prior to study commencement. This webinar series will look at the whole processing chain, as I mentioned, from exploration through to market, and how to financially engineer, and the focus there is on financially engineer projects and operations for better performance. The solutions we present will not only improve financial outcomes, but also the social and environmental outcomes of projects. We'll discuss through examples how to include these solutions in the operation and optimisation of mineral processing facilities, as well as project development from study through to design and construction. So the webinar series is in 6 parts. Today we'll talk about some examples of how the landscape is changing and some technical solutions and tools. I've already mentioned the criticality of setting up for success by developing financial analysis and engineering in parallel for study success, and part 2 will discuss this in further detail. Part 3 of the series will discuss one of Ausenco's specialities, low-cost design and high-value-add projects. Part 4 will look at project execution. Transitioning from study to execution requires detailed consideration of all aspects of scope, so good planning is a very necessary part of delivering success. We'll talk about some examples of problem solving and adding value to operations today, but in more detail, part 5 of the series will consider some of the more refined aspects. Lastly, optimisation is a key part of the process of staying in business. And the last part of this series will address opportunities for optimisation, large and small. So how are things changing and what are our challenges? What I'm showing you here on the slide is inflation-adjusted curves of copper and gold price. price is not something that we can control. Therefore, it's very hard to anticipate how that can impact on project development. But there are things that we can anticipate, and these 4 graphs show some of those factors. The top left-hand corner graph shows the amount of copper produced from SXEW as a function of overall copper production. And you'll note that that's actually declining, and that there's a much greater emphasis on concentrator production of copper, and that the concentrator feed grades are dropping, the ore's getting more competent, and technology has to step up and address the issues that we're seeing. And that comes in many forms. It can come through new technologies, different working practices, as shown in the graph in the top right-hand corner, or it can come through scale. And the bottom graph on the right shows the development of gearless motor drives over the last 30 years, from 5 megawatts through to the current nearly 30 megawatts, and 35 megawatts is possible. But the environmental and social landscape has become the key issue to be addressed for projects. And we all know of the tailings dam failures that have occurred, and social license to operate now defines the direction of our business. Processing methods and tailings containment practices need to change to meet expectations. Stakeholder engagement has therefore become the key issue. For example, the Church of England Investor Mining and Tailings Safety Initiative represents more than $12 trillion of investment in our industry. And we need to manage our stakeholders to meet their expectations. So what will be the industry response over the next few years? Will tailings dam failures increase the trend up, or will we move to address those factors? And Grant will talk about some opportunities there later. So focusing questions for moving forward. How do we exceed social expectations? Because it's not going to be enough to meet them. To meet them in the future, we're going to have to anticipate the changes and address the future needs. And how can technology and these new approaches address these needs and result in a net increase in revenue? I provided an example in the graph there of discounted cash flow for a project, where we looked at an original project, we looked at a reduced capex approach, and we looked at a range of new technologies that are available to us that incurred a slightly higher capital cost, but greatly increased the net present value of the project over mine life, looking at aspects of not just revenue, but capex and operating cost to model the project to a successful outcome and an appropriate NPV. So having said that, I'll hand over to Grant, and Grant will kick us off with a discussion on how to reduce tailings risk and water consumption.
Thank you, Greg. So today I'm going to have a look at pre-concentration and the ability of pre-concentration to reduce tailings liabilities and water requirements. So in this short, can you go back, sorry, to the previous slide? In this short presentation, I'm just going to try and convince you that pre-concentration is the best way to reduce water consumption and reduce tailings liabilities. And obviously, water and tailings aren't an issue for all mines, but they can be a significant issue for many mines. And this image on the right there really shows the kind of areas, the arid environments where a lot of mines are. This is an image of the Andes Mountains, and their water consumption is a large risk associated with social license to operate. And when I've shown you that the pre-concentration is the best approach to reducing water and tailings, I'll introduce an approach and methodology that we use at Ausenco to evaluate one of the technologies that can be used here, bulk ore sorting. So yes, you can go to the next slide, please. So this is just an image of a way of presenting the mining value chain. So at the top there in the darker blue, we've got how the ore travels through the mining value chain, and the lighter blue at the bottom, we have how water interacts with that. So from the left, the ore is first blasted, then there's grade control. Traditional grade control defines what is waste and what is ore that is then dug and driven to the crusher. The ore is crushed and then passes through a number of processing steps of milling and separation. The water is added at the beginning of the milling stage and is required due to the recovery aspects. There's technology, dry recovery isn't available for all ore types. And then the water is recycled through the thickener and fed back from the tailings as well. So what can we do to reduce the water requirements of the tailings liabilities of a conventional processing circuit? Well, firstly, in a conventional processing circuit, you have the dilution and loss that occurs with grade control. So there is loss of ore and dilution of the ore with waste that occurs with conventional grade control. And what can we do to reduce the water? Well, we could increase the recirculation of water there, but that accumulates impurities in the process that can change the delicate balance of chemistry that occurs within flotation and leaching. And to reduce the tailings, what kind of levers do we have? Well, we could dewater the tailings to produce a stable dry stack tailings, but the cost of that is prohibitory in a lot of cases. So really, with the conventional circuit, we don't have many levers to pull in terms of water and tailings. However, pre-concentration is a really good example of what can be done in terms of reducing water and tailings, in that instead of the conventional grade control, which defines waste, we can have different technologies along the way that produce waste streams when that material is liberated. So these technologies can range from bulk ore sorting through particle sorting to coarse particle recovery, either in flotation or through density. And this provides a number of different benefits. Firstly, we can create a higher grade going into the milling circuit, which allows you to run at a lower throughput and reduces the amount of water that's required for the processing, and also lowers the water consumption in it lowers the amount of tailings produced out at the end of the circuit and lowers the water consumption. It also provides a number of waste streams, coarse waste streams that can be used as with co-disposal of the tailings to provide some stability to those tailing streams. However, in a brownfield expansion, we wouldn't necessarily want to feed the mills with less material. Actually, the optimal NPV is going to be found when we utilize that capital that is available there. And if we're expanding the mine, this is the more likely approach that we've utilized to great extent, in that we can lower the capital cost of the expansion instead of going a conventional expansion where we add additional ball milling, additional milling stages and recovery stages. We can utilize the existing capital and add capital in the pre-concentration at the front end. It results in higher revenue and a lower water per metal product and a lower tailings per metal product as well. So that's the approach that we tend to look at from an Ausenco point of view. One of the things I'll go into now is just talking about bulk ore sorting, and I've got a quick example here. I used Lego just so that I had some time to play with my kids over this time, putting together a representation of what mining heterogeneity looks like. So bulk ore sorting, for those of you who know, it leverages spatial heterogeneity of an ore deposit that is then translated, and time-based heterogeneity to separate out the low-grade material. So if you look on the left-hand side, the Lego there is really showing different ore grades within the blocks. So each block represents a different grade. Obviously, red represents high grade, and the green represents lower grade. So you do have this spatial variability around ore deposits. Now, the measurement of that I'll talk about in the next slide, but it's important to measure that spatial heterogeneity. When that is dug and transported to the mill, that spatial heterogeneity is translated into a time-based heterogeneity that you can see at the top there, where different grades are fed to the mill at different times. And obviously, we want to fill up the mill with more of the red blocks rather than the green blocks, and reduce the amount of green blocks that are going to the mill. And that's where the technology really comes in. So we can use bulk ore sorting to separate out packets of low-grade ore before they get to the mill. And we can use different technologies to do that. There are different sensors available. We can use X-ray fluorescence, PGNNA, and magnetic resonance. They all have their place, have different. Some are surface level, like X-ray fluorescence. Some go through the full deposit, the full rock, like PGNNA. And some measure minerals rather than just elements, like magnetic resonance. So they've all got their place, and it's important to find out which technology fits in with which ore deposit. If you go to the next slide. So in terms of measuring the in situ heterogeneity, there are a number of ways of doing this. One may be to just change your block size in your block model. That gives you an indication of the heterogeneity, but because kriging is used in the block model, it really smooths out that heterogeneity. So what we tend to do is look down a drill core and measure and look at downhole data or diamond drill data that has the grade at different intervals, and that's represented on that graph on the left-hand side. This is from a project that we recently reviewed this on, and you can average out the grade over different distances. So the bars there represent the grade at 1 meter intervals, whereas the line there represents the grade at 16 meter intervals. So the 16 meter intervals are essentially the size of the blocks that would be used for grade control. So we can use that to indicate what kind of grade, what kind of material would be going towards the mill, and what would be classified as waste from grade control. And then the 1 or 2 meter intervals would be used, are the kind of packets that would be used for sorting. So we can use this graph on the right-hand side, which is a release analysis that measures the cumulative metal passing and the cumulative mass passing. And you can see there that there's an ability to be able to accept at least 90% of the material in about 60% of the mass. And we can incorporate that in with modeling techniques, which we'll show you now, where we can incorporate grade control and bulk ore sorting together with conventional milling and separation to optimize the MPV for different projects based on the mine plan. And what we found is that the optimal MPV is found when you sort the material that's near cutoff grade. So you can see that by the two graphs in the bottom there. And we could play around with the accept rate to find an optimal MPV, which is that graph on the right-hand side. In this study, which was on an Andean copper deposit, we found the optimal accept rate was close to 50% there. So yeah, once we bring in that understanding in with the modeling, we can find the optimal. And the takeaway messages, bulk ore sorting. Sorting is the best way. Pre-concentration is the best way to reduce your water and reduce your tailings. We can look at the in situ heterogeneity as that translates into time-based heterogeneity, do the release analysis on that, and produce a model that can allow you to optimize NPV based on those different constraints. So that's what we do here at Ausenco. Next, I'll pass you across to Tim, who's going to talk about geometallurgy.
Thank you, Grant. Hi, everyone. My name is Tim, and in my little section, I'll be talking about how a lot of the operations support that we do at Ausenco can lead to different initiatives. And my slides are about how our support for one operation evolved into a neat little geometallurgy exercise and the benefits that translated to for this particular operation. So what we're looking at here is a time series of a couple of months worth of flotation recovery. And what you can see is there was a period where flotation recovery started to decline. And that decline continued and was sustained for a period of about a month. It amounted to about a 12% loss in recovery. So it was a very difficult time for everyone who was involved. Because in that period of a month, that translated to obviously hundreds of thousands of dollars of loss. Eventually, the operation recovered, and once the dust had settled and we're able to figure out exactly what had gone wrong, in retrospect, it turns out that during the worst of this period, the feed to the concentrator was comprised of about 25% pyrite. And for those who are not flotation operators, just quickly, pyrite is quite a harmful mineral to flotation. It can disrupt the chemistry of the flotation slurry. It itself can float and dilute the concentrate. And so for the feed to be comprised of 25% pyrite plays quite a major constraint on concentrator performance. The questions that were asked obviously were how did this happen? How could this have been allowed to have happened? And when you do a root cause analysis, what you find is that a lot of decisions are based on the outputs of models. And it turns out that the recovery model that was used at this particular site had a lack of metallurgical inputs. The end result was that the model was unable to predict the onset of those low recoveries. And in conjunction with that, it turns out that sulfur assays, which are an indicator of pyrite content, were not used or not measured in the grade control samples up at the mine. So these two factors conspired to, I guess, produce that fairly nasty surprise where recovery dropped by a significant amount over a period of about a month. But they also prompted quite a nimble little geometallurgy exercise, which the operation is now benefiting from, and that's what I'll be talking to you about in my slides. So geometallurgy can mean lots of different things to lots of different people, and if you keep up with the literature, if you attend conferences, you'll see that geometallurgy can come in many different flavors. It can be implemented at many different scales, but ultimately what's common is that if you're using your knowledge of the ore body to drive good decision making, that is a key outcome of geometallurgy. Key to geometallurgy are the characterization methods and the characterization suites that are out there. And very, very broadly, you can categorize these into two buckets. You have mineralogical characterization methods, as well as, in my mind, what I call metallurgical characterization methods. And if there's one thing that you walk away from after this little section, it's that you need both. You really need both. If you fall into the trap of only doing metallurgical characterization, you might, at the end of your exercise, end up with a database of, for argument's sake, bond work indices with very little context to the numbers. By doing both mineralogical and metallurgical characterization, you'll be in a better position to link mineralogical markers to the process response of your material. So in doing this, by understanding the mineralogical drivers of this particular site, that enabled us to develop a new recovery model, which you can see with a solid black line. And importantly, this recovery model, this new model, was able to predict the onset of those low recoveries. And additionally, the recovery model was able to detect that a key proxy for pyrite, which is measured at the concentrator, is the sulfur to copper ratio, indicated by the orange line. And you can see that as the sulfur to copper ratio increased, that drove recovery down. So it was a nice outcome, and it changed a lot. Quantifying the effect of pyrite changed recovery forecasts. It allows to recalibrate processing strategies for different passes of ore, which had now been identified as being problematic. It affected the mine plan because it allowed us to reevaluate the value of different regions of ore now with this new knowledge kind of encapsulated in the form of a new model. It improved blending strategies. It also kicked off a business case for having sulfur assays measured on grade control samples. So this geometallurgy exercise kind of spiraled into a number of different follow-on initiatives which have provided benefit for the site in question. So that's it for me. Geometallurgy or future ore testing, whatever it is you want to call it, is key to making good decisions, whether that's at the planning stage, at the mine, or for those of us up at the concentrator. And having concluded my slides, I'll like to pass on to my colleague Rajiv, who will be talking about process control and digitization.
Thanks, Tim. Good afternoon, all, or good morning, or good evening, wherever you are. I'm currently based in Vancouver, and it's great with technology right across the world. And so I'd like to share some of my thoughts and insight on how can we operate smarter. These the next few slides are some of the insights we've gained and some of the strategies we've implemented to operate smarter with data, as well as a better understanding of, as Tim pointed out, the resource definition, how that can be used to better define strategies going forward. Next, please. So I borrowed Grant's Lego blocks just to emphasize the point. So as Greg pointed out, in the past, we used a small hammer, or the scale of mining was a lot smaller. Currently, we're using a bigger hammer or a sledgehammer, so the scale of mining is a lot larger, larger equipment, bigger, bigger power draws, as Greg pointed out with the GMDs. So, what does the future look like? Are we going to look at a complicated future with a complicated flow sheet, or do we want a pragmatic future? As Tim pointed out, better understanding of the geometallurgy, and as well as Grant pointed out, insights gained right back to the resource definition. You can have a better strategy in how you're going to be operating the plant. Next. So the vision for a pragmatic future is some 5 key points there, which I believe we need to drive the value through an integrated approach. So right from the resource definition all the way through the concentrator and to tailings discharge and the water consumption and the waste deposition, it all plays a major factor in that integrated approach. In our experience, a lot of the underperforming operations are not getting the basics right. So the key focus should be going back to the basics. Training is paramount to that. Understanding the constraints is integral to that. Knowing what's driving the capacity constraints, what's driving throughput, what's driving recovery, as Tim pointed out. 4th point is stability, and I think it's a key point to process control and any type of control when you have variable ore sources, and which is driving high variability in terms of throughput and recovery. How can we stabilize it? So that needs to be a key focus. And lastly, it's all about pushing the asset. I mean, there's no point having a 20 megawatt mill if you can't really fully utilize it. So the objective should be fully utilize the the power draw, fully utilize the assets, what's installed in the flow sheet. Next. So how do we unlock the value? So the key message here is it's all about understanding the interdependency of the data and then how it drives value. So going right back to the resource definition through geometallurgy understanding, redefining the resource definition based on grade control, as Grant pointed out, and how that drives productivity in terms of what are the strategic changes we need to implement in terms of process control and optimization, and what impact will have in terms of the overall utilization availability. And for example, if you're pushing throughput through your SAG mill, your wear rate's going to increase. So what are your relining strategy going to be? And how does it impact the overall availability of your SAG mill? The fourth point is constraint, which is a key point which not many people particularly look at. It's a lot more focused on the equipment itself, but it has a key integral focus, because if you can't push throughput downstream, there's no point pushing throughput upstream. And all talks to the overall efficiency. That's what we're driving, trying to minimize the dollar per ton of product. So in our experience, a lot of the insights what we gain, and in particularly looking at the optimization work, we only look at a fraction of the data, and Excel is a great tool for that. And basically we're turning 20% of that data into 80% of the value. And in current technology such as big data and AI tools, there's a place for it. But in terms of real value, in my experience, it's only adds a fraction of that overall value. So this is an example we presented at MillOps. This is the work the optimization we undertook at FUCAM. This is for PANOS. It's mainly centered on the main constraint was the SAG mill, and was driven by a combination of optimizing the liner design and redefining the process control. It had advanced process control. And there's an example here. I mean, even though we can tune the advanced process control and train the models, and there are instances where, when it was transitioning from low SG ore, which is predominantly diorite, and transitioning into high SG ore, mainly magnetite, you had this huge fluctuation feed rate and power draw. Mill just goes into instability mode, unstable mode for a brief period, and that has a big consequence in overall throughput. So we know SG has a big impact. And how do we quantify it? Because a lot of the control is driven by weight, and so the objective was, how can we measure that? The obvious one is, okay, can we go back to the mine schedule and quantify when this parcel of high SG ore is coming through? But the immediate solution, what we found was, next, please. It's a volumetric scanner. It's off the shelf. It's largely used in the bulk industry. So we installed it on the SAG weightometer, and it was just measure the volumetric feed rate, and then your quantified measurement of weight on that same conveyor, and so we can infer the SG. So we fed this information to the SAG mill advanced process control. So now we can control the water addition to the SAG mill by volume instead of by weight, and it greatly improved the stability of the mill. Next one is all about challenging the paradigm. In time and time again, it doesn't matter where you're working in Southeast Asia or Africa or South America. Every operating mine have their own habits and how they think they should be operating a SAG mill or a crusher or a flotation circuit. This is the work we undertook at Penasquito. It's presented at the SAG conference last year. So it's a complicated flow sheet and a combination of second crusher feed, pebble recycle plus HPGR product feeding into SAG mill. So the overall strategy changes how you operate that SAG mill. But that was the main constraint. Again, SAG mill was highly congested, and the solution was how can we understand the risk and then push change the paradigm how you operate that SAG mill. Next, please. So we trialed with a higher ball load and low rock filling. We understood that there are going to be some increased level of liner impact, but we understood that what the maximum operable speed should be. We quantified it, we calculated, we quantified it with physical measurements, and then we operated and greatly improved the energy efficiency, and had a consequence of that increased feed rate. One of the key things what we timing, and when you're particularly looking at control of processing circuits, process plants, is control, having good control and understanding the variability and how it has a direct impact in overall production and throughput and so forth. This is a graph generated by one of my colleagues, Carl. It's a pretty neat graph, just demonstrating how the objective here is to try and minimize that target to the max constraint. So the max constraint will be the physical constraint of that equipment, the maximum throughput we can achieve, or the max velocity we can operate that segment. So this is one is looking at, it's over to on the left when you have a lot of instability, high variability, and so the average throughput is much lower. So through instrumentation upgrade, calibration, control tuning, you're pushing that target closer to that constraint. And over to the right, that's where the future is, I believe. It's dynamic constraint, where we can feed in, as Tim pointed out, geometallurgical data and a good understanding of the parcel all coming through, as Grant pointed out, with different sensor technology, and training the models. And then you'd shift the constraint to adapt to the new feed type. And this is where the real power of these big data AI tools are going to be. It's fully dynamic constraint operation, which you can feed in other information such as cost and operating cost and constraints, etc. So linking technology to value add. In our experience, most of the value is over to the left. Doing the basics, benchmarking, simulation, having a good understanding of the integrated approach. The next stage was looking at the technology drivers, such as smart sensors, real-time analytics, remote operation with good decision making. These will add value, but it's a marginal when you compare to the overall short-term value drivers we're looking at. And over to the right, it's where what the industry wants: safer operation, virtual force, and the overall objective is it'll add value, but in the context of when you're particularly looking at production, focus on throughput, when you're focusing on NPV, it's over to the left. The short-term gains pretty much drive large-term values. So how can we operate smarter? So the three main points are focus on the value. So getting the basics right, get the basics right. Now, understand the constraint, focus on stability, and push the asset to the limit. Gain insights using good data. Emphasis on good data, because there are some bad. You should be able to distill good from bad. But it's using that insight of how can we turn 20% of that insight and 80% of the value. That is the real insight. And lastly, we shouldn't forget about the future of mining is all about leveraging of technology, remote operation. There more and more mine sites are moving to remote locations, and workforce are getting a lot more expensive. But we shouldn't forget that. But we need to have a sensible approach: how we use data, how we use that to apply it. And lastly, I see that it's enabler to push the limits of the asset, and how it should be used to train next generation controls to deal with high variability. With that, thank you for listening. Thank you.
Thanks, Rajiv. Thanks, Tim. Thanks, Grant. So we've got a few questions, but we can always do with more because we've got plenty of time left. Excellent management on behalf of our presenters. So please send those questions in using the dialogue box. But we'll kick off with our first one. So first question relates to methodology for pre-concentration, Grant. You mentioned bulk ore sorting. What other options are there apart from bulk ore sorting for pre-concentration?
Thanks, Greg. Yes, in terms of the different, can you mute yours? Thanks. In terms of the different technologies, there's a number of different technologies that can be used. I talked about bulk ore sorting, which takes into account the time and space-based heterogeneity, but different technologies take into account heterogeneity on other length scales. So there can be size-based heterogeneity, which might be the natural deportment of grade to the fines, which just requires a simple screen. And CRCO have been looking at that for a while, and we've incorporated that in some of our analysis as well. Then there's also particle-based heterogeneity at a finer scale. You can do particle ore sorting that maybe utilizes X-ray tomography or color to incorporate that. And then there's also coarse particle separation technologies such as dense medium cyclones, mag separation, and of course coarse particle flotation, which is on the finer side of the pre-concentration, but we've used that to great extent at a number of different sites where separating it at that 400 to 500 micron range prior to flotation and in the middle of a grinding circuit can add significant value put downstream. So yeah, there's a number of different ones, and it depends on the definition of heterogeneity there.
Thanks, Grant. So I've got some questions coming in. I've got one here for Rajiv. Do you need to be at site to improve process control and plant performance? Obviously, being at site's a bit difficult these days.
Yeah, so thanks for the question. Well, yeah, so currently we are managing 2 sites remotely. One of the sites in Africa, it's a bit of a challenge. They got old control systems, and but we still remotely dialing in, diagnosing remotely. I mean, a lot of the control system you can do that remotely. So the answer is yes, but there are challenges where you want to touch, feel, and smell, and so we are leveraging off this RealWear headset. We recently purchased it, so we can actually send this a piece of gear to site. If the site has Wi-Fi enabled in various parts of the operation, it talks directly to a webcam, and so you can actually dial into it, and you can visually see what the operator is seeing, and they can provide feedback. So, well, we are about to trial it at a site, and there's the same site in Africa. So, yeah, I think it's possible. Given we have to work with the best available technology what we have so far.
Thanks, Rajiv. And got one here for Tim. So, this is a good one, Tim. How do you demonstrate the value of geometallurgy management? Obviously, that's come from an operator who is having trouble getting their boss to spend money.
I think the first step is to maintain good communication channels and relationships with colleagues upstream at the mine, the geologists as well, obviously, because what that will better enable you to do is to map out retrospectively performance periods of the concentrator with different ore types that have come through at different periods, and the degree of granularity to which you can do this will depend on how much data and how good the data is that is available. So with the case study that I presented, we were able to get down to a level where using models we could actually disentangle all the competing effects of operational variables as well as the ore upon recovery. And once you kind of disentangle everything and isolate the effect of these different operational versus feed variables, we could see that when throughput increased by a third, like a typical swing and increase over a period of a week or several days, recovery might drop, say 2%. But when the pyrite content swung from one end of the spectrum to another in this period of, again, several days to a week, recovery could swing up and down by 15%. it's really quite remarkable. So and that was a level of granularity that we were able to kind of achieve with this particular case study, because we had good data and we had good open communication channels with our colleagues upstream. But I think to demonstrate the value to management, that's the first step, mapping out retrospectively performance periods of the plant with the parcels of ore that are known to have been processed at those times, and that's a first step on a long geometallurgical journey.
And I suppose that works where you've got large variance in performance. But, you know, if you're an operator and you've been operating the same way for 30 years and the plant's equipment is declining and maybe it doesn't match the new ore body, how do you know whether there's an opportunity there? And then how do you explain to management the extent of that opportunity?
Well, that's a hairy question, Greg. How do you know? I guess test work needs to be embraced, and whether that test work is done on site or at commercial labs, that is a way of assessing process response for different ores under controlled conditions, and identifying what ores may or may not be problematic. But you're right, it is probably easier for operations that do experience these highly variable ore types to justify geometallurgical initiatives. But I guess, in my experience, every site or every concentrator will complain about the various ore types and the wide variety of ore types that they do have to process. So perhaps perhaps it's easier for a lot of concentrators to justify than what they might initially think.
Thanks, Tim. So there's a question here I'll file at Grant around, what type of companies are chasing the less traditional approaches? And so in your experience, what do those clients look like, Grant?
So there is a wide range. I mean, even the small small mining companies are incorporating this, and small mines are incorporating pre-concentration. I mean, Ravenswood Gold Mine incorporates pre-concentration where there's deportment of gold to the fines, and there's a number of different small mining companies that actually find it easier to incorporate things like particle-based sorting because of the throughput constraint of that. A lot of larger mines will struggle to incorporate that within their circuit. But in terms of bulk ore sorting and coarse particle flotation, a lot of the majors are looking at that at the moment on a lot of their deposits, and looking at that in a really robust way across a number of different geological types, ore types, commodity types. There's even really fine-grained deposits can benefit from pre-concentration in some form or another, as well as the multi-elemental mines. It can be used to, instead of rejecting waste, it can actually be used to segment the ore to go to different processing routes. And yeah, pre-concentration can be used in a number of different ways for different clients. So I guess it can be used across the board as far as I've found, but in different ways and in different drivers are motivating the use of pre-concentration. That answers the question.
Thanks, Grant. Got a question here for Raju, just to share them all around. Raju, how do you deal with data when it comes in from a client, and how do you manage the expectations of clients in terms of the quantum of the improvement?
Good question, Greg. Yeah, so as Tim pointed out, so it's if you have good data, you can make better decisions. So some sites, they lack sufficient amount of say process controls. This example here is the site in Africa. I mean, they have control system, but they don't have any sort of historian, so you can't actually capture real-time information such as pi. And so we have to. It's a slower process to understand what the constraints are and how can we make better decisions. But it all relies on building that trust up front with the site team, with the operational team, because you are relying on their insight. Given the current circumstance, we cannot travel to site. We're relying on their insights and their experience to provide insight. And then we feed that into our benchmarking tools and models and say, based on a particular ore type and hardness or competency, this is the expected throughput and at a particular grade, and this is the expected recovery. So having good data and good baselining is important. And then looking at the next stage is, okay, so given the availability of data or the volume of data, how the equipment's being utilized. In the cases for Penasquito, we did some measurements. We know, okay, so the mill is a bit congested. So we demonstrate, okay, if you run it at if you understand what the risks are, you should be able to increase increase the ball charge and reduce the rock load, and then you should be able to operate at a lot more efficient way of operating a SAG mill. And we demonstrate it. So that comes with the trial process. And once you demonstrate it, then you have to buy in, okay, this is the expected throughput we can push through that circuit if we do all these changes.
Another question on ore sorting, which seems to be very popular when it comes to questions, but there's always space for more if there are still people who have some questions to ask. So a question here around multi-element deposits, and how does ore sorting relate to multi-element deposits, particularly from a greenfield's perspective? How do you address them? What are the options that are available, Grant?
So I guess for a multi-element, I kind of covered that a little bit with the previous comment in that it might be that there's different processing routes for different elements, and ore sorting can be used to direct different grades or different components in different directions prior to the processing plant. But it can also be used as a way, different pre-concentration strategies can be used in combination in multi-element, where you can do, say, a roughing style stage with bulk ore sorting up front, where maybe that looks at all sulfides or something like that, and then a more cleaning stage following using particle sorting. That's been used in a number of different projects. In terms of greenfields and how this applies to greenfields, I think it depends on the pre-concentration technology. So in terms of bulk ore sorting, the key there is measurement on the ore body. So the in situ heterogeneity at those different scales is incredibly important. But when you start getting into density separation or coarse particle flotation, then modeling of that that technology within the circuit becomes much more important, and those models have to be element by size models with the required degree of complexity to be able to assess the financial benefit of those and the best way to operate them. So that's how we kind of split it in the work that we do. The measurement is much more important for that kind of bulk ore sorting, and then the modeling is much more important for the coarse particle flotation or the density separation. Hope that answers your question. Both of those can be done in greenfields, I guess.
Okay, I've got one last question here from Sam Palladini. So he's asking about pre-concentration again, Grant. A lot of interest in pre-concentration. With small to medium plants, how do you maximize the value when you have potentially high capex implications for small to medium plant-based projects?
So once again, it kind of really depends on the deposit. We're doing some work at the moment, and the position of the deposit in its life cycle. We're doing some work at the moment for a couple of clients looking at small to medium-sized plants where there's satellite deposits. They're trying to assess the viability of bringing in additional satellite deposits from that have large trucking distances, 80 kilometers, 100 kilometers from the mine. And in those cases, the ability to pre-concentrate dry at the mine and then transport higher grade material those longer distances towards the plant, it adds a lot of value. Now, how we do that pre-concentration is obviously something that we'd look into on a deposit by deposit basis, and what kind of technologies we use there are very important. But yeah, it's still very important into the small and medium-sized concentrators, and yeah, critical to be able to get the ore prepared correctly for the mill.
Yeah, there might also be some modularisation opportunities on smaller plants that don't avail themselves to larger projects. So, you know, it can be an advantage to be a small operator if you've got a number of different deposits, and you know, that suits modularisation in some form. Okay, well, we've still got a little bit of time left, but I've run out of specific questions. So I'll just ask my fellow contributors whether there's any final statement that you'd like to make. Tim, do you want to kick off?
Characterize. That's there's always value in understanding what you're feeding your concentrator. There's value in understanding what you shouldn't feed your concentrator. So while it might take some effort, it might involve some logistics. You know, once the benefits start coming through, no one ever really questions the cost. So.
Great.
Yeah, I guess the key from what I was talking about is that if water is a concern on your mind, or there's concerns around the tailings legacy issues and risk associated with that, the pre-concentration is a direction that should be pursued, and that's going to give you biggest bang for buck, and that we have the ability to be able to measure that now for greenfield. We don't have to install the measurement on site in a brownfield kind of application, but we can measure that heterogeneity in situ and model that and provide an outcome that optimizes NPV.
And last but most importantly for the operators listening, Rajiv, any final statement?
Yeah, so as I emphasized in my last slide, the importance of getting the basics right. It's amazing that simple things like, you know, not maintain ball charge level or not regularly checking the density. These are these small things which can drive stability, increase the performance, and you know, as Tim pointed out, measurement is a key factor in it. Understanding how that ore is going to respond to the plant performance is a key metric. But it's also, finally, it's about achieving stability. Good process control, it's all about stabilization. It's as a primary objective. Thank you.
Thanks, Rajiv. And just to add to that, you know, obviously maintain those instruments, because as you pointed out during your presentation, you know, good data is the background to making improvements and success. So thanks to the team here for their input today, and thanks to AusIMM for facilitating this presentation. If there are any further comments or questions, then please feel free to send emails through to any of us, those who know us at Ausenco, or through the AusIMM.
Okay,
so,
perfect. I would now like to bring the webinar to a close. So thank you, Greg, Grant, Tim, and Rajiv for taking the time and energy to present today. I would also like to thank everyone who attended and those who are viewing the recorded webinar. I hope you found the presentations insightful and you will join us for future AusIMM webinars. Thank you once again, Grant, Greg, Tim, and Rajiv. Enjoy the rest of your day.
Thank you.
Bye-bye, everybody.